Off the coast of Vancouver Island, a piece of the planet is coming apart. Not a crack in the ground, not a new fault. An entire slab of the Earth's outer shell is tearing loose from the slab beside it, and one section has already dropped roughly 3 miles below its neighbor. This is happening at the northern end of the Cascadia Subduction Zone, the fault that runs 700 miles down the west coast of North America and is capable of producing a magnitude 9 earthquake and a tsunami that would reach the shore in minutes. That fault is not simply sitting there loading up. Part of it is falling to pieces. And the strangest part is what that might mean, because a subduction zone that is breaking apart is a subduction zone that is slowly switching itself off. The engine that builds the largest earthquakes on Earth appears to be losing a section, which could make the worst-case scenario smaller than we thought. It does not, however, make it simpler, and the way we found all of this out involves a ship dragging a 9-mile-long microphone across the Pacific. Start with how you look at something buried under an ocean and then buried again under miles of rock. You can't drill to it, you can't photograph it. What you can do is shout at it. In 2021, a research vessel spent weeks crossing the waters off Vancouver Island, towing an array of underwater sensors that stretched roughly 9 miles behind the ship, longer than most cities are wide. The vessel fired pulses of sound down into the seabed, and the sensors listened for what came back. Every layer of rock down there reflects sound a little differently. Sand answers differently than basalt. A rock slab answers differently than a fractured one. Collect enough of those echoes from enough angles, and a computer can assemble them into a cross-section of the Earth's interior. The technique is the same principle a hospital uses to look at a baby, scaled up until the patient is a tectonic plate. When the team processed those echoes and published the result in the autumn of 2025, the images showed something nobody had ever seen directly before. The oceanic plate sliding under North America was not simply bending down into the mantle the way the textbooks describe. It was splitting. One structure ran for about 22 miles, a long tear cutting straight through the slab. Beside it, the seafloor showed a vertical step where one block of plate sits about 3 miles lower than the block next to it. And this was not a wound near the surface. The fractures sliced down through the sediment, through the crust, and into the mantle underneath. The earthquakes told the rest of the story. Along some stretches of the tear, small quakes kept firing, which means the two sides are still touching and grinding against each other. Along the stretches, the rock has gone quiet. Not calm, quiet. And the researchers reading those images suspect that in those silent sections, the plate may have already finished separating. Quick thing before we go under the seafloor. If this is your kind of story, subscribe and tap the bell so the next one reaches you. So why is a slab of rock the size of a country tearing itself in half? Because Cascadia is not one clean plate diving under North America. It's a patchwork, and the pieces are not moving at the same speed. Down the long central stretch of the fault, the Juan de Fuca plate slides toward the continent at roughly 1.6 inches per year, about the rate your fingernails grow. Up at the northern end, that plate gives way to a much smaller fragment called the Explorer plate, and the Explorer is dragging its feet. It moves at closer to 0.8 inches per year, and some sections appear to be slower still. Take a sheet of anything and pull 1/2 twice as hard as the other, and it does not stay a sheet. The material twists, shears, and eventually splits along the line between the two. That line has a name. The Nootka Fault Zone, a boundary separating the fast plate from the slow one, and the seismic images show it sharpening across the edges, narrowing from a broad, messy band of broken rock into a focused corridor about 12 miles wide. Zoom out in time and the pattern becomes clearer and considerably stranger. For the last 4 million years, this corner of the Pacific has been shedding pieces. Fragment after fragment has torn away from the main plate and started moving on its own, becoming what geologists call microplates. The Explorer plate is one of those fragments. It was not always a separate thing. It became one. And these fragments have a family history. The Explorer, the Juan de Fuca, and the Gorda plate to the south are not independent characters in this story. They are the last surviving scraps of a single enormous plate called the Farallon, which once stretched along the entire western edge of the Americas. Over tens of millions of years, North America rode over it and swallowed it almost whole. What remains offshore today is the tail end of that plate, a few slivers still sinking, still being consumed. So the tearing up there is not a sudden malfunction. It is the closing chapter of something that has been dying since long before there were primates. And every time a piece breaks off, the machine gets weaker. A subducting slab does not sink because something pushes it. It sinks because the cold, dense rock already down in the mantle pulls the rest of the plate along behind it, like a tablecloth sliding off a table under its own weight. Tear away a section and you cut part of that pull. The plate that is left behind sinks a little more reluctantly, which makes it easier to tear again. A machine that is failing in a way that accelerates its own failure. Which finally brings us to the question everyone in Oregon, Washington, and British Columbia actually wants answered. If the northern end of Cascadia is coming apart, what does that do to the earthquake that region has been bracing for since anyone thought to look? The honest answer has two halves, and the first one is genuinely reassuring. The largest earthquakes on this planet are produced by long, continuous faults, and that comes down to simple arithmetic. Magnitude is not really about how violently the ground shakes at any one spot. It's about how much fault surface breaks at once. Rupture a short segment and you get a serious earthquake. Rupture 700 miles of locked interface in a single go and you get a magnitude 9, several minutes of shaking, and an ocean displaced. That last part is what makes megathrust faults uniquely dangerous. When the interface finally slips, the edge of the continent lunges upward, lifting the entire column of water sitting on top of it. Models of a full Cascadia rupture put the first waves on the Oregon and Washington coast within roughly 15 minutes, which is less time than most people would need to understand what had happened. There is no outrunning that from sea level. Every mile of fault you remove from the equation is a mile that cannot contribute to it. So anything that shortens the fault or chops it into disconnected pieces works against the worst case. That is what the tearing appears to be doing. The researchers modeled what happens if the explorer fragment detaches completely, and the result is something called a slab window. The sinking plate is simply gone from that stretch, leaving a gap, and hot material from deeper in the mantle flows up into the space where the slab used to be. There is no longer a plate diving under the continent there, which means there is no longer a fault that can rupture there either. Their estimate is that this would remove roughly 47 miles from the length of the Cascadia Subduction Zone, about 1/12 of the whole thing. A section of the most feared fault in North America would quietly cease to be a fault at all. That is a real result, and it is the reason the team's own announcement carried the phrase that this is not necessarily bad news. A shorter subduction zone has less surface to break, and less surface means a lower ceiling on the maximum earthquake. If you live on that coastline, the northern boundary of your worst case may be retreating. Now for the other half of the answer. A fault that is falling apart is not a fault that is calming down. In the short term, it's doing the opposite. All that fragmenting produces a tangle of new faults inside the broken plate. The seismic images show fracture networks cutting through the crust and into the mantle beneath, and those fractures are not decorative. Each one can generate earthquakes of its own on steep faults that slide sideways rather than thrusting. Such earthquakes are smaller than a megathrust and rarely raise a serious tsunami, but they're shallow, frequent, and sitting under populated coastline. There is a second complication that matters more. Segmentation cuts both ways. A subduction zone divided into pieces may struggle to rupture end to end, which is good. But those same divisions concentrate stress at the boundaries between segments, and the northern portion of Cascadia is widely regarded as one of the most tightly locked stretches of the whole fault. Simplifying the maximum magnitude does not simplify where the next rupture starts. There is a reason we can't speak about that locking with any confidence, and it involves looking down rather than out. Scattered along the coastline are ground stations tracking their own position against satellites overhead, accurate to a few millimeters a year, and radar satellites map the shape of the land from orbit with smaller precision. What those instruments show is a coastline being quietly dragged inland and squeezed. compressed like a spring by the plate wedged beneath it. The rock is not sliding, it's storing, and every year that passes without release adds to what is stored. And the scientists themselves are careful about how far the result reaches. The tear is confirmed where the survey lines crossed it. Whether it continues farther inland under Vancouver Island itself is inferred rather than proven, because the northernmost line did not extend far enough to see. There are open questions about whether hot mantle rising through the gap explains certain volcanic fields in British Columbia. This is a finding that opens more doors than it closes. So the accurate summary is neither comforting nor alarming, which is usually a sign you're close to the truth. The ceiling on the worst possible Cascadia earthquake may be a little lower than we assumed. The path to getting there is messier than we assumed. Both statements are supported by the same set of images. Step back from the coastline for a moment, because there is something larger in these pictures than a regional hazard map. Humanity has known that plate tectonics exists for about 60 years. In that time, we have watched plates spread, collide, slide, and dive. What nobody had ever properly watched is one of them die. Subduction zones are not permanent. They start, they run for tens of millions of years, and eventually they shut down. And the shutting down has mostly been something we inferred from old rock long after the fact, the way a coroner reconstructs an event from a skeleton. This is different. Off Vancouver Island, we now have direct images of a subduction zone in the process of failing, not the aftermath. The event itself rose in at one instant in a process that runs for millions of years, which happens to be the instant our species developed the instruments to look. It's worth appreciating how narrow that window is. The tearing has been underway for around 4 million years and will keep going long after everyone alive is gone. Human civilization occupies a sliver of that so thin it barely registers. We arrived, invented seismology, built a ship capable of imaging rock 4 miles beneath an ocean, and pointed it at a plate that happens to be dying right now. And this only happens here. Earth is the only world we know of with active plate tectonics. Venus has a stagnant lid of crust, one unbroken shell. Mars has the same. On both, the surface is a fixed thing. Only on this planet does the outer layer break into moving pieces that build mountains, recycle the crust, drive the chemistry that keeps the climate habitable, and once in a very long while, tear one of their own apart. So the Cascadia Fault really is falling apart, and the headline really does cut both ways. The northern end is fragmenting. A piece of oceanic plate has dropped 3 miles and is peeling away from its neighbor. If that separation finishes, the stretch of the fault will stop being able to produce great earthquakes at all, and the maximum size of the disaster that region has been preparing for may shrink. That is a genuinely good outcome, delivered by geology rather than engineering. But the rest of Cascadia is untouched by any of this. The main stretch remains locked, still loading, and it has not released a great earthquake since the winter of 1700. The fault is not being canceled. It is being shortened at one end while the rest of it waits. We know that 1700 date with startling precision, and the way we know it is worth a moment. Along the coast of Oregon and Washington stand groves of dead cedars, killed when the ground dropped and seawater flooded their roots. Their tree rings show they all died in the same season. Meanwhile, on the other side of the Pacific, Japanese officials recorded a tsunami that arrived one January night with no local earthquake to explain it. Matching those two records gave us the night the fault last broke, more than 7 decades before the United States existed. If you want the full picture of how that waiting compares with the other monster on the American West Coast, we broke down Cascadia against the San Andreas in an earlier video. And the difference between them is bigger than most people expect.